Hello, everyone. We have with us today Olivier Groux from Keyboards, who will give a presentation in this session titled Up Close, an Emerging Recycling Technology for the EV Future. Olivier currently works as Project Manager, Battery Specialist at Keyboards, Switzerland. He is responsible for the process, development, and implementation of a system for separating the various components of used lithium batteries without chemical or thermal treatment. He also worked at DSM Nutritional Products as chemistry laboratory technician in the range of synthetic research and in energy consulting for the city of Bern, Switzerland. Thank you, Olivier, for joining us here today.
Thank you very much for this kind introduction. And I'm very happy to be here and to talk about our battery recycling process. Firstly, I would like to introduce the company Keyboards, then to talk a little bit about the cycle life from our vehicles, and then a little theory about batteries and cycle life to understand later on our recycling process. So who we are like a little company in Switzerland with 180 employers, founded in 1991. And the CEO is Martin Keyboards. You can see him sitting on the vehicle. We have a little different products, like we have the most common one is the postal delivery vehicle, the yellow one, but we also produce, like for private person, the 3 wheels and 4 wheels. We have utility municipal vehicles and also fun vehicles that are a little bit faster with nice acceleration, and also an off-road version. And all together, we have like a fleet management system where we can put this in our vehicle to have parameters like the location or the consumption of energy and a lot more of parameters. We have more than 22,000 vehicles around the world that are daily in use. And the battery that we are recycling at the moment, we installed them in 2009. If we have now a closer look to the vehicle life cycle, we produce them in Switzerland, and the use is very environment friendly because firstly electrical, so it's very clean. Then with our system, with the stop and go, the post delivery is very fast, and the vehicle itself needs a low maintenance. At the end of life, we have now a new project that we make a second life vehicle of them. This means that we are taking the part and we can reuse like 70% of these parts again and making a new vehicle. And if we have like a closer look to the life cycle of the battery, we are taking this apart, we are making new capacity tests, and we saw that like 60% of all the batteries that are used in 2009 have a rest capacity of over 80%. So the state of health is over 80%. This means we are giving them a new life in the second life vehicle. And the 40% have a capacity of 70 to 80%. And now we are doing like energy storage system with this. And after the battery have a lower state of health of 50%, we are recycling the batteries. So now which battery do we use? We have the prismatic cells, the plastic ones. And if we have a closer look, you can see that most of the cells are produced the same way. So you have an anode, a cathode between the separator, then a metal case or a plastic case. We have now a plastic case, the newer ones have a metal case inside the electrolyte. Which chemistry do we use? We choose LFP cells because of 3 reasons. The cycle life are much higher than NMC or NCA. Also for the environment, it's better to use LFP because we don't have any cobalt or other rare material. And one of the main reasons was the safety. So if we have like a short circuit inside the battery, the valve open, we have smokes coming out, but the temperature reached 200 to 250 degrees and doesn't burn. And therefore we choose LFP cells. Now a little slide for understanding how the recycling works. I just want to talk about the cell voltage. So you have here a little green square, and this means that the battery should work between 2.4 volt to 4.2, 4.3 volt. And if you go lower than that, or if you go higher than that, you are destroying the cell. So it's good to stay in this range. And here a very short introduction how a cell is produced. So in the first step, you are mixing the coating paste. And then you are putting the paste on the aluminum or copper foil and you are pressing them together. In the second step, you are going through a drying process and then you are pressing them again and measure the thickness of the aluminum foil and the copper foil with the active material on it. The next step is like cutting the foils. In our case, it looks like this. After this step, it's the winding. Most of the producers are making now the winding like this. So you have one big foil from each and you're winding them all together like this. In our case, we have the set folding system. This means we have the cathode and between then the separator and then the anode. And these steps go further on like this. Then you're putting all together in a case, you're closing it, you're filling up the electrolyte and you do the first aging process. And after the aging process, you can sort them, make a ranking and see which capacity do you have. So now the recycling, how we do it. Or like firstly in general, in Switzerland, they are collecting the batteries, then they are shredding the batteries, and then they're using the pyrolysis method. This means we are melting the batteries. With this method, you are using a very high energy and the recycling quote, it's not that high. It means you reach between 40 and 60% of the recycling quote. There is another method, like the hydrothermal recycling method, that you are using, you're solving the materials, and the recycle quote, it's very high, it's over 90%, but in general, the usement of the solution are not that environment friendly. And you can also mix both methods, but also there, the energy consumption is very high. So what we do, we go for a direct recycling method. And these are the main parts. And we start with the storage and preparation of the cells. And a lot of people think that's not a very important step. But I showed you before the slide with the range of the cells. So we have a special way how to discharge the cells to 2.0 volt. And with this method, we are taking a lot of energy out of the cells, but we are not destroying the cells. And the safety is for the co-worker or for the operator, it's not any more dangerous to work with the cells. So the energy is out and we didn't destroy the cells because we stopped at 2 voltage. The next step is taking apart the electrodes. This is the machine we developed. It works on solar energy, so very low energy consumption. And I have a little movie how it works. So we can put 4 cells at once. And then we are cutting the top of the cell. Then we are drilling a hole in the case and ejecting the whole electrode pack outside of the case. This step is manually. The separator is on the top and we are rolling up the separator and separate the anode and the cathode. So at the end we have the separator, the cathode and the anode, but still with the active material on the top, on the foil. The capacity we can recycle 3 tons per week with this machine. So now how to take the active material away from the foils. Because we didn't destroy the cells before, and the first step of the production of a cell, the coating paste, they use, in our case, a binder that are water-based. So now we can put the electrode inside the water, and without energy, the active material gets separated from the aluminum foil or from the copper foil. And here a little movie. So this is water and the cathode, and you can see here, without energy consumption, the active material get separated from the aluminum foil. This is real time, and the cathode was 20 seconds inside the water. And if we take the whole plate, it looks like this. So at the end, we have from one cell very clean aluminum foils. We have lithium iron phosphate. We have the separator, the graphite and the copper foils, and of course the plastic case. With this method, we can recycle, our recycling quote is over 91%. What we cannot recycle at the moment, it's the electrolyte inside. And the next step will be closing the loop with these materials. Thank you very much for your attentions. And if you have some question, I will ask. Yeah, thank you very much. Can you still hear me? Yes? So the question is like, which one is cost effective? I mean, we are using the direct recycling methods. I cannot answer these questions. I never tried one of these methods. Is there another questions? Yes, we did the test with NMC cells, and depending, like the first step, it works. The second steps, depending on the binder material, we did some tests and it works with NMC cells, but for that we need further researches. Yes. Our battery have a capacity of 100 amp hours to 270 amp hours, and the machine was constructed that we can all kind of prismatic cell from our batteries, we can recycle all of them, like from 100 to 270 amp hours. Yes. That's a difficult question, I think. We prefer LFP, lithium iron phosphate batteries. I think the trend will go there. I mean, Tesla and Volvo are changing or are also starts installing the iron phosphate battery. Also for the buses, they are using a lot of buses are using iron phosphate battery, but I think the NMC and NCA will still be in the market. For the requirements, our idea is like to produce like the machine that you saw. We developed the machine as little as possible to build the machine also in a 40-foot container. So the idea from us is that we are transporting the recycling to the country like Australia or other countries, that not the battery that are dangerous good, that they have to come to our company, so that we are putting the recycling to the other countries. Was this the questions? And how they're stored? Like still in a charged way, and like the temperature between room temperature like 20 to 25 degrees. That this is the method we do it. Okay, thank you very much. I think the next session is started. So thank you very much for the invitation. See you next time.
Thank you very much, Olivier. Thank you. Bye-bye.
Bye.